I'm gonna start recording. Um, Copy link address into chat, copy link address into chat. There we go. Okay, so now there is I wish I could pin that or something. But at any rate, we are going to go ahead and jump into that. We are on slide number 4 of this slide deck, where we were talking about protein purification. So at this point in time, we've talked about enzymes. Those are your biological agents of change. Those are the proteins that catalyze reactions. They can take reactant one and produce a product. Now, we have also talked about proteins that do not have any sort of catalytic function. For example, hemoglobin. Now, we've also looked at specific examples of enzymes when we talked about glycolysis. So that's kind of the rationale for why we've taken the journey that we have so far. Now, what we are talking about in this is imagine that you had a very complex mixture, like the contents of a cell, where you've got sugars, you've got proteins, you have genetic material like DNA and RNA, you have minerals, you have this very complex mixture of stuff. And what you want to be able to do is just study something, like one thing within that complex mixture. And in order to do that, you have to go through a lot of separations. So could everyone give me a 7 in the chat if you follow what I'm getting at there, or follow what I'm saying? Okay. Now I know a couple more folks have joined, so I'm going to just add to the chat. There is the slide deck that we're using. Okay, awesome. So it's good that you understand that, because if you understand that kind of conceptually, then we can get into kind of the weeds of how would you do that. Now, so whenever you're purifying a protein, you're taking that complex mixture, basically the contents of a cell or the contents of um, lots of burst cells, and you are doing some sort of treatment to cause a change that makes one component of that mixture or one part of that mixture become either soluble or insoluble. Now, with that in mind, whenever you do this sort of separation, you always want to be quantifying it. And what I mean by that is you always want to be keeping track of kind of different numbers. So we'll So just kind of conceptually, when you're purifying a protein, one of the most important things for you to follow and understand is if you're purifying an enzyme, that enzyme that you're purifying needs to have some sort of activity. And whenever I say that, I mean it needs to be something that you can measure. For example, does anyone remember the enzyme hexokinase? Hexokinase is able to convert glucose to glucose 6 phosphate. Now, if you, let's say hypothetically, you used a UV light source and you shined UV light at a cell extract or something, and you adjusted the UV light source to say, I'm just going to pick a number within the UV range. Let's say that you adjusted it to 682 nanometers. I randomly came up with that number because it's within the UV range, but let's imagine that glucose 6 phosphate was able to absorb light at 682 nanometers. Now, could you give me a W in the chat if you have ever heard of the Lambert-Beer law, also known as Beer's law? Okay. Now, does anyone remember basically what Beer's law was used for? And if you want to unmute yourself, you're welcome to. If you can type it up quickly, awesome. Um, Beer's law is very powerful because it has an equation that is roughly A equals epsilon path length times concentration. But more than that, and I'm guessing there's at least one person who's typing this up or typing up a quick summary, it allows you to detect a substance, a molecule, whatever, in a solution. Could everyone give me a P in the chat if, yeah, that's kind of what I remember it to be? And any other character if you've never heard of the Lambert-Beer law. Okay. So this right here is a very powerful method and technique that biochemists use very often. Now let's go back to my example. I'm going to give you this kind of hypothetical situation where we're using glucose 6-phosphate, and we're going to say that that molecule can absorb light at 682 nanometers. And let's say that it uniquely absorbs light. So nothing else in a cell extract absorbs light at 682 nanometers. Is everyone with me there? Give me a 1 in the chat if you're with me. Okay. Now, what you would want to do is, the reason this is kind of a valuable idea is because if you have, I'm going to say a whole cell extract, which would be our crude cellular, I'll change it to crude cellular extract, CCE. Let's say that you have CCE from, I'll say E. coli, and let's just say you have water. So you have two samples. And with these two samples, you shine light at 682 nanometers at them. So you are looking for glucose 6-phosphate. If this glucose 6-phosphate is present in there, then some of that light that you shine at that sample will be absorbed. Now, in water, would you expect there to be any glucose 6-phosphate? Give me a 0 if your answer is no, and give me a letter if you think, yeah, there's probably glucose 6-phosphate in water. Okay. So we wouldn't expect, if you got distilled or deionized water, you wouldn't expect any glucose 6-phosphate in there. And so you would expect your absorbance at 682 nanometers to be 0 because there's no glucose 6-phosphate in there. Does everyone follow me there? Give me a Y or an N. Okay. Now, let's say in E. coli, which does indeed have hexokinase. Let's say that you measure the absorbance to be, let's say it's 0.987. And I'm giving you a hypothetical absorbance, but I want you to respond, what does this tell you about the presence of glucose 6-phosphate in this E. coli sample? Is there some yes, Y, or is there none, N? Yeah. If we see this number be anything but 0, we would expect there is indeed some glucose 6-phosphate there. Now, if we see glucose 6-phosphate in there, that kind of indirectly tells us that there is indeed hexokinase in there, because hexokinase is our enzyme that produces glucose 6-phosphate. Could you give me a 5 in the chat if you follow that, an A in the chat if, wait, that was too much of a jump, I don't follow? Okay, great. So I want you to operate with that idea because that is the principle on which you make a column like this, enzyme activity, that shows that indeed there is some enzyme activity. Now, this number right here, this 0.987, It's an absorbance value, so it has no units. So this isn't nanometers, this isn't concentration. That number you could use to plug into the Lambert-Beer law and determine a concentration. And then there's more involved in that. That concentration can be used to determine enzyme activity or quantify enzyme activity. But for the time being, what I want you to do is look at this and say, okay, well, this activity number is coming from the use of the Lambert-Beer law. Could everyone give me a Z in the chat if they follow that, or a slash in the chat if they don't follow that? Okay. So I'm going to erase some of this. And now I'm just going to ask, does the activity column make sense to you? Give me a wired end to the chat. Okay. So this column right here tells us that indeed we do have some of the desired enzyme activity that we are looking for. And whenever we are trying to purify something, we'll go through a number of different treatments. This table shows us some examples. You can try to precipitate proteins or precipitate enzymes. You can try to separate them based on charge using ion exchange chromatography. You can separate them based on their size or molecular weight. And then finally, you can separate them based on their ability to bind something, also known as affinity chromatography. At this point, what I want you guys to know is I want you to know that chromatography is a technique that's used to separate things. We're going to get into those specific different types of chromatography in a moment. I also want you to know about activity and okay, well, that's derived from a like monitoring an enzyme's activity. Now, the takeaway from this is or this table right here is something that I want you to kind of come back to. But the most important takeaway from this is that you are doing a great job purifying an enzyme if your total protein goes down and your specific activity goes up. Specific activity is saying, well, how much of your enzyme is present compared to the total amount of protein? So I got a private message. So the light absorbance in the previous example is the measurable activity. It's a kind of through the Lambert-Beer law. Yes, that would be a fair. Does that answer your question? Perfect. Okay. So when you think about, oh, how pure is a protein? I want you to think about specific activity. The higher your specific activity is, the more pure your enzyme is. Now, when you have a complex mixture, you're going to start out with a ton of protein, a ton of junk, more or less. And what you want to do is get rid of the stuff that's not yours. For instance, if you're trying to purify or isolate hexokinase, do you care if there's hemoglobin in that sample? No, that's not what you're looking for. Okay, now your takeaway is if the desired protein is an enzyme, then your amount is quantified as your activity, and purity is known as your specific activity. Now, I tried to explain this same sort of principle the other day using like candies, but here we've got two different beakers. This beaker here on the left is considered basically your whole cell extract, or what is your crude cell extract, your CCE. And all of these different marbles or balls represent different proteins. If you're trying to enrich for or isolate the red balls, well, let's take a look at it. This crude cell extract, I see 1, 2, 3, 4, 5. I see 5 red marbles. How many total marbles do you see? Well, I see about, I don't know, just for a round number, I'll call it 100. I'm not counting those or anything like that. But then over here, or actually, sorry, before I do that, actually, yeah, I'm going to go over to the other column. Here, what we have is, well, let's count them up. 1, 2, 3, 4, 5. 5 red balls out of, ooh, that looks like, I'm going to call it 20. total proteins. So your specific activity measurement here in your crude cell extract is about, I'm just going to use a percentage. I'm going to say that my protein is 5% pure, and my specific activity, I'm going to call it 5. Is everyone good with those numbers? Give me a Y or N in the chat if you follow that. Because I'm comparing my enzyme of interest to the total collection of proteins in that beaker. Now, my second beaker, I've got 5 of my enzyme of interest out of 20 total proteins. Okay, so 20 total proteins. If I were to make that a percentage, I'd say, well, it's 25% pure. And then, no, yeah, 25%. I would say that my specific activity is just going to say 25. Now, both of these numbers, my specific activity of 5 and 25, my specific activity has gone up. What has happened to the total amount of protein in my beakers? Well, that's gone down. When you look at this, I mean, I want to give you another example that kind of illustrates like if your purification was perfect, what you would have is 1, 2, 3, 4, 5 red marbles, and that's it. You'd have a total number of 5 proteins, and all of them would be your 5 red marbles. In which case, your specific activity, well, 5 out of 5 would put you at, well, 5 divided by 5 is 1 times 100. We're looking at 100% pure. Does everyone follow those kind of splits and those breakdowns? In which case, also our specific activity might be listed as 100 or something like that. Okay, so whenever you're trying to purify a protein, your aim and objective is to see that specific activity continue to increase with every subsequent step. Now, activity is 5. Okay, there we go. 19, my numbers are a little off. Okay, so a mixture of proteins can be separated using a number of different techniques. It's helpful for me to think about this in terms of like candy, in part because I like candy, but also I can think about things like, okay, well, if I have Skittles, Skittles have unique properties that are different from M&Ms, which are different from peanut butter M&Ms, which are different from peanut M&Ms. Proteins are represented by all of these different candies. Different proteins have different charges. We know that because different amino acids have different charges. Proteins are different in size. You know, you might have a protein that's 75 amino acids long, and then another one that's, well, 1,600 amino acids long. Affinity for a ligand. When have we talked about ligands? What's an example of a ligand that we have mentioned previously? I'll give you a hint. When we were talking about proteins and ligands, oxygen. O2 is an example of a ligand. Now, do we know of a protein that loves to bind oxygen? Yeah. Hemoglobin. Hemoglobin and myoglobin are great examples. And I want you to think about versus hexokinase. Let me ask you this. Do you think that hexokinase has the same ability to bind oxygen, O2, as hemoglobin does? Give me a wired end to the chat. Yeah, they don't. Hemoglobin and hexokinase, they have different functionalities. So they're going to have different affinities for different ligands. So if you had a mixture of hexokinase and hemoglobin and you wanted to select for one of them, well, either get glucose because hexokinase is going to bind to the glucose, or immobilize oxygen because that hemoglobin is going to bind to that oxygen. Other techniques include separating based on solubility. So if a protein is a soluble or a cytosolic or it stays in solution, if a protein has a lot of hydrophobic residues, and then temperature stability. So these are all different techniques and properties that you can use. Sorry, these are all properties that you can use different techniques on to separate proteins based on. Now, chromatography is commonly used for preparative separation, in which the protein is often able to remain fully folded. So what that means is when you do chromatography, and specifically the way that biochemists typically do chromatography is column chromatography compared to like thin layer or gas chromatography. So column chromatography is used by biochemists. And the great thing is whenever you use that technique, your protein is enriched and you can still, use it for whatever function you want to use. Okay, could everyone give me a 1 to 7 in the chat? A 1 if, yeah, I'm good with this. A 7 if you are just completely sideways. And you can send it as a private message. Now, the techniques that we're going to focus on, let me rephrase that. The chromatographic techniques that we're going to focus on will be used for separating proteins based on charge, size, affinity, and to a lesser extent, solubility. Okay. So the first technique that I want to talk about, column chromatography. One of the important things about column chromatography is that, well, this is kind of what the column looks like. These 5 different snapshots of it are showing the column as things progress through it, as a sample progresses through it. Now, whenever you think about chromatography, you're probably familiar with a mobile and a stationary phase. Now, the mobile phase is what is going to have the thing or the protein that you want to capture in it. So that would be like your crude cell extract. The stationary phase. The stationary phase, I always think about it as the thing that gets modified to grab either, I'm just going to say proteins because we're thinking about proteins from the mobile phase. Okay. So when you're doing column chromatography, you're going to have, I'm going to call it our crude cell extract in a Erlenmeyer flask or in a source, a reservoir, and you are going to use a peristaltic pump. And basically, that pump is going to pull the solution from your reservoir and add it to the top of this column. Now, right here, this kind of grayish mixture, that's to indicate your protein sample is being loaded onto this column. Now, over time, your mobile phase will flow through this column, and different components of that mobile phase will separate. Different proteins will separate, and they will separate from one another based on how attracted they are to the stationary phase. So how tightly does the stationary phase bind them? Now, with that said, let's look over here at the end. This last display, we've got blue, red, and green. Think about these as being 3 different proteins. Now, one of the challenges of column chromatography as a biochemist is you don't really have the advantage of your proteins having any sort of color to them. I know whenever I took organic, we separated fluorine from fluorinone. And those were 2 different compounds that one was like a neon or like a yellow, and one was like a neon green. And so you could visualize it, you could watch them move through, and you were separating based on polarity. Now, here we have this mixture of A, B, and C right here. Right there. Okay. A, B, and C are right there. And as time proceeds and as this pump flows solution through, A, B, and C will begin to separate. And the separation will become greater and greater and greater. At the bottom of this column, you would have little test tubes. Test tubes that maybe they collect 1 milliliter, they collect a small volume. Now, let me ask you this and add to the chat, which protein is going to come off of the column first? Is it A, B, or C? C. You're absolutely right. Now, let me ask you this then, as kind of a follow-up question. Which one of these proteins, A, B, or C, has the least affinity for the column? The least affinity for the column. If it has a high affinity, it's going to grab on and hold on to it. So our least affinity would again be C. I kind of think that most of y'all were anticipating that I was going to say which one of them has the most affinity for the column. And that's why you answered A. And I'm not trying to be like, ooh, shame. That's not my point. But does everyone understand? Give me a Y or an N. Does everyone understand why A has the highest affinity? Or, yeah, how A has the highest affinity? It grabs onto the stationary phase and stays there for the longest, which is why it is kind of moving through the column most slowly. C, by comparison, oh, between A, B, and C, C kind of moves through the column pretty quickly. It's almost like it's at a dinner party and it has no one to talk to. I always kind of think about this as like three friends or something like that get out of a car and they go to a party, and friend A is the one who just loves talking to everyone. Oh, tell me your life story. Friend C is the person who's like, I'm here. I had to make an appearance. Hey, 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 hey. And they make it through that party very quickly. B is the one who's like, yeah, I got to move through it, but I'll talk to people periodically. Could you give me a 1 if you follow that for A, B, and C with respect to affinity and the rate that they migrate through the column, and a 5 if no, you don't follow any of that? Okay. Now, at this point, we haven't talked about anything regarding the stationary or the mobile phase and the properties of those stationary or mobile phases, but we're getting into that right here. Okay, separation by charge, ion exchange chromatography. I will tell you there are two different types of ion exchange chromatography. There is cation exchange chromatography, and there is anion exchange chromatography. Those are your two major types of column chromatography or ion exchange column chromatography. Now, I like this snapshot because this zooms in on these gray balls that represent the resin. So that's our stationary phase. Now, could anyone add to the chat with the symbol, what is the charge of our resin as it's depicted here in this kind of cutout? Yes, it's negative. Okay. So that negatively charged stationary phase, what is that primarily going to bind to? And add the symbol. Absolutely right. We see that represented by these blue balls. These blue balls have both, well, it has a pair of positive charges and one negative charge. We've got charges on there. Positive charges are going to draw this protein to bind to our resin. Okay. Now, what that means, this protein right here, positively charged. Would you call a positively charged protein a cation or an anion? C for cation and A for anion. Yeah, it's a cation. Now, what that means is if you are trying to capture cations, you need a negatively charged resin. So when it comes to cation exchange chromatography, cation exchange, and whenever you hear that term, cation exchange, the stationary I'll change this, with cation exchange, comma, your stationary phase is negatively charged. This statement right here, can everyone confirm? Yes, I will learn that with a Y in the chat. Okay. Now, if this is a true statement, then my question for you is, what is the charge of proteins that will bind to an anion exchange chromatography column? And I'll start working on this statement. With anion exchange chromatography, and I flipped it a little bit. With anion exchange chromatography, your stationary phase is positively charged. Therefore, I'll change that to it will bind negatively charged proteins. Okay, so if this is at all helpful, one of the ways that I think about this is I think about the activity of fishing. When you go outside or when you go to a lake to go fishing, what are you trying to catch? Give you a hint, it starts with an F and ends with an ish. Yeah, you're trying to catch fish. Cation exchange chromatography. You are trying to catch cations. How do you catch cations? Well, you catch it with a stationary phase that is negatively charged. If you're doing anion exchange chromatography, you are trying to capture or catch anions. How are you going to do that? With positively charged, or a positively charged stationary phase. Could everyone give me a Y or N to the chat if you follow that? Okay. Now, what that means is that anytime you do column chromatography, specifically ion exchange chromatography, let's say that you have a column. I'm going to draw my column right here. And then here's the test tube of the proteins that float out. If I have a cation exchange column, and here's the very first sample that I collected. Okay, so I have my reservoir flowing in here. It's a cation exchange chromatography column. So my stationary phase is negatively charged. So positively charged proteins will get captured. Let's say that the very first sample that flows through my column are the proteins in here in the very first sample. What do you think their charge is going to be? It's a cation exchange chromatography column. Add to the chat. Are the very first ones going to be negatively charged or positively charged? Negatively charged. You're absolutely right. Because their affinity for the column was basically zero. So the cation exchange chromatography, negative proteins or negatively charged proteins don't delay. Oh man, Melanie, that's a fantastic question. So when you're purifying a protein, you're going to have tons and tons of fractions that you collect. They're going to be like 1 milliliter each. And when you do this, what you have to do is you have to go and have a way to test every single one of those fractions. So if we were to go back and say we're trying to purify hexokinase, And we saw that hexokinase came out in this very first fraction on a cation exchange chromatography column. What did we learn? Well, we learned if we see hexokinase activity in this very first fraction, we would say, oh, well, our hexokinase that we were trying to capture has an overall negative charge. Okay, cool. Good to know. Now, it's entirely possible. So to answer your question, it's not necessarily the first or the last because you're going to collect you might collect 75 fractions. Does that make sense? Give me a wire and that first part that there's lots of fractions. You might go through them and say, "Oh, okay, well, my hexokinase activity was in fraction number 4 or 39." Okay, Melanie, that's a great question. So the thing is, if you look at, like, let's take this chromatography column right here. The dark red proteins are going to come out in, say, fractions 3, 4, and 5. The light red, they're going to come out in fractions, let's say, 10, 11, and 12. Then these, maybe 20 to 23. And then these last ones might be in fractions 30 to 39. In terms of how pure they are, well, you don't have to worry about these proteins right here contaminating those down there. Does that make sense? I think, well, yeah, oh, I get it now. So in theory, when you get to fraction 39 that you find out, oh yeah, that's where my hexokinase activity is, chances are you don't have a lot of other stuff in there. Okay. Now, when it comes to purifying a protein, this gives you one piece of information. If a protein goes straight through a cation exchange chromatography column, you have learned something about it. If it goes through and it doesn't delay on a cation exchange column, you'd say, okay, well, the column itself was negative. It has an attraction for positive proteins. My protein went straight through. Therefore, my protein is negatively charged. Now, give me a 7 in the chat if you follow that. Okay. Now, when you see a protein with a negative or a positive charge, that should make you think about different amino acids. So let's tackle our first poll question here, which is, which protein would most likely bind to a cation exchange column? Is it a protein that's rich in leucines? Is it a protein that's rich in histidines, alanines, or aspartic acids? Okay, so to deduce this, cation exchange, that is we are looking for cations, so positively charged proteins. So in order for a protein to have a positive charge, it's got to have, well, positively charged residues on there. Leucine, nonpolar. Alanine, nonpolar. Histidine, it's polar. Aspartic acid, it's also polar. Histidine is a polar positive. Aspartic acid, polar negative. So we would expect that if we have a protein that is adhering to or binding to a cation exchange column, we're going to have lots of histidines on that protein. Could anyone add to the chat what other amino acids would we expect to be in high abundance on a positively charged protein? Give me the single letter codes. Well, if we expect the protein to be positively charged, we expect to have positive or polar positive. Jordan, absolutely right. Lysine for K and R for arginine. We would expect these amino acids to be more common or more abundant than, well, aspartic acids, for instance. Okay, I'm going to go ahead and close that question. Next up. Okay, so that's ion exchange chromatography. So if you're thinking, what do I need to know about ion exchange chromatography? You need to know that it's separating based on principle, that there are based on property of charge. You need to know that a cation exchange chromatography column is negatively charged to bind positively charged molecules. You need to know that an anion exchange chromatography column, well, the stationary phase is going to be positively charged to bind negatively charged proteins. Then it's also important to think about, well, if we're looking for a protein with positive charges or a protein with negative charges, what do we expect to see? Positive charges, we expect to see histidines, lysines, or arginines. If it's a negatively charged protein, therefore it's going to bind to an anion exchange chromatography column, we're expecting lots of aspartic acids and glutamic acids, D and E. Okay, now our next separation technique is known as size exchange chromatography. This is also known as gel filtration chromatography. Now, what this does is it separates based on size of the molecule. Now, when we measure proteins, we always refer to them kind of based on their molecular weight, which is kilodaltons or kDa. So, just to give you a little bit of an idea, one amino acid is roughly 107, or it's an average of 107 daltons, which is the same as 0.107 kilodaltons. Okay. So if you have a protein that's 100 amino acids long, then you're talking about something that's, well, 100 amino acids is about 10.7 kilodaltons. Now, proteins range from 10 kilodaltons to, 275 kilodaltons. They can be massive. Now, what's important to know about size exchange chromatography, also known as gel filtration, which I always write GF, but I don't want people to think about it as gluten-free chromatography. Gel filtration chromatography separates based on molecular weights. And check this out. We've got proteins represented by purple, orange, and green balls. Which one of them are the largest? Green. Those are our highest molecular weight proteins. Now, what do you notice about these protein samples at the bottom? Which one of them came out of the column first? The largest first, absolutely. Now, that's always something that to me, I struggled with, and it was very confusing for me. But what's what I've been able to do to think about it that made sense to me was if you look at, okay, just like what we had here, we had these resins, and the gray ball represents a resin or represents a little bead that makes up our stationary phase, also known as our resin. Here we've got these same beads, but what I want you to notice about them is that these beads have holes. Okay. Now, you can separate based on molecular weights, and here's how I personally think about it. I'm going to give you three examples. Let's say we have a basketball, a let's go with a softball, and a marble. Okay. So if you can imagine, let's say, could you give me a one in the chat if you're familiar with those big buckets that you can buy over at Lowe's or Home Depot? Okay. So I'm thinking of these blue buckets and you can fill them with water, you can mix things, people put cement in them to make like I don't know, posts and whatnot. Okay. So let's imagine let's imagine this bucket is Small enough, or it's large enough that the softball and the marble will fit into it. The basketball, however, will not. Imagine, if you will, the basketball, what it's going to do is it could either get stuck in the top of that bead, or stuck in the top of that hole, or what I want you to imagine is that somebody shoots it and it rims out. Basically, it doesn't fit into that bucket. So what happens to it is it just kind of like nopes out of the bucket. And therefore it gets to the bottom, it gets to the ground first. Does everyone follow that? Because it doesn't even enter this bucket. This bucket being the holes within these beads, or it's my example for the holes within the beads. Could you give me a Y or an N if that makes sense? If you follow me. Okay. Now, large proteins never even enter these beads, never even enter the pores within these beads. So they just kind of move past them altogether. Now, the softball and the marble. The softball and the marble will both enter this bucket. And whenever they enter the bucket, what's going to happen is they're going to adhere to the interior side of that bucket. And in order to get through, they're not just going to like jump on the side and slide down. Instead, what they're going to do is basically be in contact with that bucket the whole time. Does everyone follow me there? That they will remain in contact with that bucket and basically kind of ride the side of that bucket in a kind of cylindrical fashion. Does everyone follow me there? Give me a Y or N to the chat. Okay, great. Now, between the softball and the softball is going to cover a lot more space more quickly. So it might only take like 5 spins around that bucket to make it through. The marble, by comparison, the marble has to go through so many more. And every single time that it circles, it takes more time, which is why our smallest proteins, our marble in this case, takes so long to get out. Gel filtration or size exclusion chromatography, you can sum it up as beads and, or sorry, contact between the proteins in the beads, largest, exit first. The longer that something stays within that bead, the smaller that protein is. Could you give me a 3 in the chat if you follow all of that? Okay. So we've got ion exchange chromatography separating based on charge. We've got size exclusion chromatography separating based on molecular weight or size. Now we're going to go to affinity chromatography. Okay, affinity chromatography is dependent on attraction between a protein and a substrate or a ligand. We talked about this with respect to hexokinase versus hemoglobin. Hemoglobin loves binding to oxygen. Hexokinase, by comparison, would bind to something like glucose, but not necessarily to O2. So your beads, just like you had with cation exchange chromatography and gel filtration chromatography, they're basically the same thing. The only difference is what is kind of, it's almost like what is stuck on there. And a ligand, a small molecule, is basically going to be sewed into that bead. And based on if something adheres to that or kind of is attracted to it, it will either move through or it will not. So what I mean by that is, let's say that our ligand here, or our immobilized molecule, is glucose. And let's say that we have a mixture of hemoglobin, myoglobin, and hexokinase. Hemoglobin and myoglobin, if they have affinity for oxygen, it's just random happenstance. It's like, oh, what a coincidence. But to our knowledge, it doesn't have it. Those two proteins have very low, if no affinity for glucose, in which case they are going to exit the column first. Okay, so those are gone first. Hexokinase, by comparison, this is one of the places where your column chromatography for biochemists is a little bit different than the column chromatography for organic chemists. Hexokinase is going to adhere to these beads. And you know what it's going to do? It's going to stay there indefinitely. And it's going to stay there until it has a reason to leave. So what that means is that you could collect, fractions 9 through 10,000, maybe 10,000, that's hyperbole, but you could collect thousands of fractions. And what is hexokinase going to do? It's going to stay bound to that glucose because it has no reason to leave. Does everyone follow me there? Give me a Y or N. Because what it wants to bind is glucose, and glucose is there. And it says, all right, I love glucose, so I'm just going to hang out here. So then a fair question is, well, how do I get the protein to release? And the answer is by adding that glucose, for example, to your mobile phase. So you flow glucose through the column. So that doesn't disrupt the glucose that is bound to your bead, but instead it just gives hexokinase something else to bind onto. Does that make sense? Give me a Y or N to the chat. And if it doesn't make sense, then please don't hesitate to say. So in affinity chromatography, you need to have that free ligand to release. Bound protein. Okay, so we've talked about 3 different major types of chromatography: ion exchange, gel filtration or size exchange, and affinity chromatography. These are all column-based and they're all bead-based. Those beads either have a small pore in them, in which case you use it for gel filtration chromatography. They have a ligand immobilized on there, in which case you're using affinity chromatography, or they have a charged molecule on there, in which case that is known as your ion exchange chromatography. Depending on if that immobilized charged molecule is positive or negative, you're either dealing with anion exchange chromatography or cation exchange chromatography. So with your different types of chromatography, how do you feel about this so far? Give me a 1 if, okay, cool, I follow that, or a 5 if you're thinking none of that makes any sense to me. And you can send the 5 if you want as a private message. Now, let's go ahead. So affinity chromatography is really based on attraction between your protein or your enzyme and its ligand or substrate. So if the ligand is glucose, then you're going to be able to really well bind things like hexokinase. Okay, now we're going to go on because this is a question people always love to ask. It's a good question. Which separation technique is the best? Separating by charge, so ion exchange chromatography, separating by size, gel filtration, or separating by affinity. Or there isn't one best, they're all valuable depending on the circumstances. I like this question because, I think that at its heart, the question is, well, why do we have multiple different techniques? And I'm going to go ahead and just say the correct answer is D. There isn't one best. Now, just to kind of illustrate that, when I was a graduate student, I was working with a bacterial protein, or I was working with a plant protein expressed in bacteria. So I was working with a recombinant protein. And you know what? All that I did was affinity chromatography. The reason for that was because I didn't need a protein to be 100% pure. I didn't need my protein to be 90% pure. My experiments were good if my protein was like 65% pure. If you need a protein to be very, very pure, then chances are you're going to use some combination of these things. So what I've seen more times than not in terms of the sequence that these different techniques are used is typically People will do separation based on charge. Then they'll do separation based on affinity. And last but not least, they'll do separation based on size. That's typically the sequence that I see, but that's not to say that's the only combination that works. Um, and the rationale or the reason for this is because when you're separating based on charge, you can basically, if you imagine that you've got kind of a diversity of charged molecules, you can get rid of 50% of your proteins. And then when you go on to do affinity chromatography, you're only dealing with a smaller fraction than what you had. So after that, you can select for, okay, well, positive proteins that bind glucose. Great. Then you go on to do size exchange chromatography. You've got your positively charged proteins that bind glucose. And let's say that your protein is 74 kilodaltons. Well, there might be proteins that do these two things that are 50, 70, 110, in which case you can get rid of these other fractions. Now, the last thing that I want to say about why you might stack different chromatography techniques, well, it's because when you stack these different chromatography techniques, you eliminate or you reduce your risk of kind of artifacts or background or kind of, yeah, artificial results or incorrect or inaccurate results. Okay, so this would help you purify and isolate your protein of interest. Now, if you do one of these things, you're still tracking your activity, your enzyme's activity. If you see your enzyme's activity cut down to zero, what do you have to say about that? Well, you probably shouldn't do that technique. So then you kind of go back and you try again. Okay, so after we've separated proteins, based on these different chromatographic techniques, we do electrophoresis. Could everyone give me a 1 in the chat if they have done any sort of gel electrophoresis in their careers? I know that in genetics lab, they typically do a DNA gel electrophoresis, and that technique is similar to protein gel electrophoresis. Now, electrophoresis is an analytical technique where you basically use an electric current. Now, with that in mind, do proteins have charges? They do. Do different proteins have different charges? Yes, they do. So we've got an electric field pulls proteins toward their charge. Could anyone add to the chat, what is the overall charge of a DNA molecule? A double-stranded piece of DNA? DNA has a negative charge. And the reason for that is because of its structure. Proteins are a little bit different. You can have positively charged proteins. You can have negatively charged proteins. So that's kind of a challenge. The gel matrix of this gel makes proteins separate based on their size and their shape. Okay. A protein gel is commonly a material known as polyacrylamide. So separation of proteins through electrophoresis is often called polyacrylamide gel electrophoresis, or PAGE. Now, what it looks like is this. Typically, protein gel electrophoresis uses a vertical gel, as opposed to DNA gel electrophoresis, which uses a horizontal gel. Now, protein gel electrophoresis uses this compound right here. Sodium dodecyl, 12 carbons, sodium dodecyl sulfate. This is a detergent. Now, the important thing about this detergent is it gives proteins a universal negative charge. Because proteins can be positively charged, they can be negatively charged. SDS basically coats a protein and gives it an overall negative charge. So what that means is now you can apply this electric current and separate them based on their size because every single protein has a negative charge. Now, what this ultimately looks like, what a protein gel electrophoresis experiment looks like is shown here. What this is showing is we've got our crude cell extract, CCE. Then we've got, well, effectively, okay. This right here is a soluble crude extract. Think about this as our CCE. These two represent controls, both positive and negative controls in experiments. This column right here represents precipitation with ammonium sulfate. What I want you guys to compare, and I want you to think about and look at the crude cell extract, the anion column, the cation column, and the purified protein. And with the crude cell extract, there's a bunch of protein in there. All of these little bands right here, and here, and here, and here, and here, 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 they all represent individual different proteins. This very robust band represents your protein of interest. So when you look at these different columns, it's pretty fair to say, oh, well, anion exchange right here, that enriched for our protein. So too did cation exchange chromatography. After all of the different techniques were applied, we have our nice robust band there. That is our protein of interest. What's the difference between the anion exchange cation and the purified protein? Well, the purified protein, chances are, is going to be after one more step, like size exclusion chromatography. The anion and cation exchanges, they help you enrich for your protein. They help you get rid of junk, other stuff, meaning all of these other proteins right here and right here. Okay. So when you go through these techniques, when you go through your column chromatographies, you then want to analyze it analyze it with a SDS page. Now, every SDS page, the most important part is represented by this first column. This shows what are known as your molecular weight standards. These have proteins of known sizes. For instance, this first one that I have a small rectangle around, that's 97.4 kDa. This one right here is about 45 kDa. This one right here is 31 kilodaltons. Could anyone tell me, based on where our protein of interest migrates, approximately how large is this protein right here in terms of kilodaltons? Well, this band is 45 kilodaltons. This band is 31 kilodaltons. It's pretty safe to say that this protein is, well, it's smaller than 45. Would everyone agree with that? Y or N to the chat. Okay. Is it larger than 31? Y or N to the chat. So if this is 45 right about here, this is 31, I would call my protein, maybe about 40 kilodaltons. Give me a 1 in the chat if you see that, if you follow that approximation. Okay. Now, one important thing to know about gel electrophoresis versus size exclusion is that these two techniques both separate based on molecular weight. The smallest proteins, every protein's loaded up at the top here, and then they migrate. And they separate based on molecular weight. With gel electrophoresis, I don't understand how it could show the same position for both anion exchange. It's the same protein that was enriched there. So I got a private message question that basically was, I don't understand the anion exchange chromatography versus cation exchange with respect to the results. So essentially, think about anion exchange chromatography as you collect, say, 60 fractions. And we'll just use hexokinase as our example. You would go to each one of those fractions and test for hexokinase. And then whenever you collect the fraction, let's say it's fraction number 28, just a random number there, that has your hexokinase activity, you would load a small amount of it here. Now, for cation exchange chromatography, again, you collect 60 fractions. You're again going to test for hexokinase. And let's say in this case, it's fraction number 10. You see that, oh, okay, fraction 10 has hexokinase. This band right here that I've drawn these little stars by, that represents hexokinase. Does that make sense? So the follow-up was, so you collect whatever you are trying to purify for regardless of the methods. Absolutely. So you use those columns and you might have a sense of, oh, well, I think my protein has positive charges. So my guess is that it's going to adhere to this column. It's going to adhere to cation exchange chromatography column. You go through and collect all those different fractions, and then whatever fraction has your enzyme's activity, that's the one that you care about. Does that make sense? Does that help at all? Okay. Okay, so I think that's a fantastic question to ask. Like, well, why would I do both? Well, the reason that you do both is it all depends on how pure you want that sample to be. So if you need it to be ultra pure, then you might do an anion exchange chromatography column, then a cation, then affinity. You might do affinity 2 or 3 times. So our protein here is roughly 40 kilodaltons because it runs lower than the 45 kilodalton band and it's higher than the 31 kilodalton band. The difference between gel filtration, also known as size exclusion, the difference between size exclusion chromatography and gel electrophoresis is that gel electrophoresis, you are not expecting, you are not using what is loaded onto that column, onto that gel. Because the protein, whenever it kind of migrates through here, this is a gel. This is a gel matrix that basically denatures your protein and makes it useless. So if you do gel electrophoresis, you're only using 1/1000th of what you have. Size exclusion chromatography, when the protein comes off of that size exclusion chromatography column, you can capture that, collect it in that fraction, and use it after that. So our migration is based on molecular weight. And you can use a chart like this, or a basically how far does something migrate and its molecular weight, and come up with a nice graph. And that allows you to say, okay, well, mine migrated, let's call that, 18.2 centimeters. Well, that migrated 18.0 centimeters is 45 kilodaltons. And then this one that migrated 21.6 centimeters, well, that's 31 kilodaltons. So you can kind of piece that together. Okay, so when you think about the techniques that we've talked about today, we've got columns. We've got basically 4 different columns: cation exchange, anion exchange, size exclusion, and affinity chromatography. For columns, you can use what, or let me say, yeah, use what comes off of the column. Then when it comes to GE or gel electrophoresis, it's not usable after the not usable after the gel. So you're not going to collect that and use that again. Okay, we've got a couple more things that I want to talk about. This technique, known as isoelectric focusing, it's going to be able to separate proteins based on their pi, or their isoelectric point. Does anyone remember what is the net charge of a protein at its pi? Just like what is the net charge of an amino acid at its pi? Zero. It's going to have some positive charges and some negative charges, but the net charge is zero. Okay. In terms of a protein solubility, whenever it reaches its pi, it becomes least soluble. So what you do for isoelectric focusing is you load a protein sample onto this kind of, it's almost like a strip of paper. And what you'll notice is that when you apply this electric current, molecules will move until they reach their pi, at which point they will stop because they're least soluble there. They will stop there, and that's all she wrote. You can do mass spec to analyze those, so you can determine the approximate mass of the molecules there. But more than that, there's a technique right here. This is known as 2D gel electrophoresis, or DIGE, which stands for differential gel electrophoresis. This does two things. The first of which is you separate proteins based on pi. So first, separate based on pi. So you use isoelectric focusing. Then what you're going to do is take that strip and put it on top of a gel. This is your standard gel electrophoresis. Can you tell me what property you're separating these proteins based on? In here. Molecular weight. Okay. So this is a technique that's invaluable because you can separate proteins based on their pi, and then you can separate them based on their weight. The result looks a little bit like this. And you might think, oh, cool, a little cute little Rorschach test. And you're not too far off. But what's great about this technique is that in the past, I don't know, this was originally a part of, or this was originally done back in the 70s, but then it kind of found new life. Because what people can do, or what researchers can do, is they can take a healthy wild type individual, and let's say they take liver cells. I'll just say liver cell extract. And they'll take all the proteins with liver cells and they'll separate them based on pi. Okay, so there's going to be tons of proteins on there. Okay, and that's not going to give you a whole lot of information. But then when you apply it to this gel electrophoresis, your proteins are going to separate based on their molecular weights. And you're going to get something that looks a little bit like this. All of these dots represent different proteins. Now, you can then compare that to cancerous cell line, or somebody who has some sort of potential disease state. And you can look at the liver cell from the healthy individual and from the unhealthy individual. And then you can overlay and compare these two. And you say, oh, okay, well, you know what? When we look at the healthy individual, we see that right there. Okay, and I can map that, and there, that's there. But then this protein, this protein, and some of the other ones are gone. What happened? So you'd say these are absent, or maybe something's different between a cancerous cell line or an unhealthy individual and a healthy individual. And you say, well, why is that? Well, if there are these differences, then there must be something about that cancerous state that's causing this. In which case, then what you do is analyze and identify what are these proteins? Are these proteins involved in sugar metabolism, fat metabolism? What's going on with these proteins? And as soon as you identify them, then you can say, okay, well, that there must be some sort of misfunction or dysfunction with that function within that um, person who in that unhealthy person. Okay, so I'm going to stop right here, but what I want you to kind of review is what have we done today? We've talked about our different chromatography techniques, cation and anion exchange chromatography. What do they separate based on? What is the importance of the stationary phase? Then what we have after that is we've got our affinity chromatography. That's separating based on ability to bind something. Then we've got size exclusion chromatography. All three or all four chromatography columns are valuable for separating and then using what comes off of those columns. Electrophoresis. Well, you can separate based on molecular weight. And then you also have isoelectric focusing where you can separate based on PI. Then you've got this 2D gel electrophoresis where you separate based on PI first and then separate based on molecular weight. We are going to jump back into this stuff on Tuesday. We're going to finish this slide deck and then we're going to talk about DNA at the end of that. In the meantime, though, thank you guys very much for coming to class. I hope that you guys have a great day. And if anything comes up, please don't hesitate to email me. I'm glad to try to set up a time to meet with you. But have a great weekend. And thank you very much for coming to class and engaging. I appreciate it.